Hello everyone, we are Engineering Numerical Analysis Team Number 1, and today we will introduce our personalized squat reference generation method based on biomechanical analysis. Before we get into the details, let's start with what a squat really is. A squat is not just bending and straightening the knees with a barbell. It is a full body movement requiring balance, mobility, and strength. Two of the most common squats are the high bar squat and the low bar squat. Even though they may look similar, the bar placement changes your postures, balance, and the primary muscles engaged. Many people ask, if I squat exactly like this athlete, will I develop the same muscles? But the answer is no. Even if two people perform the same movement, their biomechanics, such as momentums, joint angles, and muscle activation, can be completely different. This is why a personalized approach is necessary when learning or training the squat. Using individual anthropometric data, we generate a personalized squat reference to evaluate joint torque and muscle demand. You simply enter your body measurements and barbell weight. The model then computes your biomechanics and provides a personalized motion simulation and torque heat maps. There are two main assumptions in constructing our body model. First, we simplify the squat to a 2D representation rather than a full 3D model. Researches show that while performing a squat, there is no movement in the side planes, which makes the 2D model of squat quite similar to the 3D model. Therefore, we are going to use a 2D model throughout our research. Next, we model the human body as a planar multilink system, allowing us to use inverse kinematics and inverse dynamics MATLAB tools, commonly applied to robots. In this formulation, the torque computed at each joint can be interpreted as the muscle force transmitted through its momentum. Although the momentum varies with the joint angle, in reality, previous studies show that assuming it to be constant does not significantly affect squat mechanics. Therefore, our model treats the momentum as constant and uses joint torque as an indicator of muscle demand. To model the squat motion, several assumptions were introduced. First, the trunk angle θ3 is assumed constant during the motion. As shown in reference number 1, where trunk tilt was kept fixed during analysis, using a constant trunk angle is a practical modeling assumption. Second, the barbell's horizontal position is aligned with the midfoot and moves only vertically. This follows reference number 2, which states that the barbell COM should remain above the midfoot throughout the lift for mechanical stability. Third, many studies report that the barbell is positioned at C7 in the high bar squat and at T3 in the low bar squat. Based on this, the corresponding C7 and T3 heights for a 175 cm male were obtained from available data and incorporated into the model. Fourth, the bar was assumed to stay in place horizontally, moving only with the lifter's vertical motion. This is the overview workflow of our model. We construct the body model, solve the inverse kinematics, and then perform inverse dynamics for torque analysis. Let me walk through each part. We first determine the segment lengths, mass ratios, and COM positions from anthropometric references to construct a representative human model. Using these parameters, we built an individualized rigid body model in MATLAB with the robotics toolbox. To run the IK-based squat simulation, we computed the bar's vertical position at the initial and final postures using two modeling assumptions. The first one is fixed trunk angle, and the second one is vertical bar motion. These provide the initial and final bar heights and allow us to compute joint angles for IK and inverse dynamics. To get joint angle information, we employed generalized inverse kinematic function in MATLAB, which gets robust configuration, constraints, and target position, and solves inverse kinematics based on our input. We implemented rigid body dynamics in MATLAB using the standard equation of motion. By inputting the generalized coordinate vectors, the system computes the generalized torque vectors as the output. This allows us to quantify the precise load on each joint. This is the overview of our total code structure. The core objective of our program is twofold. For beginners, the system provides high bar and low bar reference motions clearly, while for experienced lifters, it delivers heat map-based torque feedback that enables precise self-correction and performance optimization. Let's start with the novices. Beginners often struggle with these questions. They lack a standard to follow. To solve this, our MATLAB code provides the ideal reference motion. We offer standardized posture data so beginners can visualize and imitate the correct form. We specifically focus on the two main styles, high bar and low bar squats. As shown in the graphs, high bar squats are knee dominant, while low bar squats are hip dominant. For numerical analysis, we compute the torque area by integrating the torque profile over time and use it for comparison. We quantify this difference. The graphs show the integrated joint torque and mechanical work. You can clearly see that high bar squats place more load on the quadriceps, while low bar squats engage the hips more efficiently for heavier loads. Here is how a novice would use our tool. Now, let's move on to experienced users. They already know how to squat, so they need optimization. First, capture your current squat posture at bottom position and compute the angles. Let's analyze this heat map. This graph represents the joint torque integration profile around the current squat posture at high bar. We varied the user's tibia and femur angles by 15 degrees to visualize how slight changes in posture affect joint loads. And this is the heat map for low bar. By analyzing this heat map, users can determine how to adjust their posture on their own. We will show you how. The optimization process begins with a choice, high bar or low bar. We must consider the trade-offs. Look at the left graph. As the arrow indicates, the deeper you squat, the more load is placed on the knees and quadriceps. In contrast, the right graph shows that a more forward trunk angle increases hip engagement. Crucially, not every range on this graph is possible. You must consider your mobility limits in the areas marked with red lines. In this zone, the angle between the tibia and femur is too small. Consequently, if torque exceeds your limit, the lift fails. Also, excessive forward trunk causes instability and shortens the working distance. Considering the limits, our tool allows users to choose their optimization goal. Feedback number 1 focuses on increasing quadriceps engagement. Feedback number 2 focuses on raising gluteus engagement while reducing knee demand. For users with weak knees, our tool suggests feedback number 2 to shift the load from the knees to the hips. By adopting the feedback number 2 posture, the user can reduce knee torque demand by 11.69% while increasing hip muscle engagement by nearly 10%. For the experienced users, first few procedures are the same with those of novice users. The difference is that if you're capable to choose your own squat trajectory, we also provide simulation for you. You just type few more parameters and execute one more simulation. Future work includes transitioning to 3D spatial analysis and incorporating nonlinear momentum modeling to enhance accuracy. In conclusion, we offer a MATLAB-based tool that supplies standard squat references for novices, while generating torque information that allows experienced users to self-correct their posture. Remember, you are not alone, just squat. This is our reference page. Thank you for listening to our presentation.